All right, so today we'll be wrapping up performance and limitations. This is part two. Part one, we talked about what performance is, what affects performance, that height, heat, humidity. Is the air getting more dense? Is it getting less dense? Pressure altitude and density altitude. Pressure altitude being our altitude corrected for non-standard pressure, and density altitude being our pressure altitude corrected for non-standard temperature. So pressure and temperature going to be really good indications of whether the air is dense or less dense. And then humidity being a factor as well. But we saw when we went through the pilot information manual, it doesn't really take account for that, but we just have to be cautious of those water molecules not helping us out with engine power, propeller thrust, or lift on the wings. Now we got to talk about weight and balance. So weight and balance is going to give us a good idea of what we can load in the aircraft, what is the max gross weight for our aircraft, what kind of loading arrangements is really going to affect our performance as well. Is it a forward center of gravity? Is it an aft center of gravity? But basically, what are we putting in the aircraft? So, it could be us, it could be a passenger, it could be a passenger in the back, baggage, tow bars, oil cans, all this stuff plays a factor in how we calculate our weight and balance and the performance that we're actually going to get. So, weight and balance for the Cessna 172 at least is just you can kind of think of it like a balancing act. So we have a fulcrum here, and then we have a plank right here. So at the moment it's kind of balanced out, but we're going to introduce some variables that would make it unbalanced. So the fulcrum here, we can kind of call that our center of lift. A lot of people also call it the center of pressure, center of lift. It's synonymous. But if we have kind of the side profile of the Cessna 172 here, we can imagine that center of lift, just for simplicity reasons, being in the center of the wing. So we have this upward force acting on the wings, and that's where we're kind of balancing the plank at the moment. Now, we know we have downward forces, weight, and that's going to be caused by gravity. Gravity's pulled towards the center of the Earth. Where is gravity focused on? Well, it actually changes in how we load the aircraft. So with the Cessna 172 at least, we always have a center of gravity. It's designed to have a center of gravity right in front of the center of lift. And this is what gives us a favorable stall characteristics. Center of gravity is basically if we suspended the aircraft by a string, where would it balance out where it was straight and level with no forward nose or aft movement. So that center of gravity is kind of situated in front of that center of lift, but it can actually move forward or aft, and that's going to give us some different characteristics with the aircraft itself. So we have a center of lift in the middle, then we have a center of gravity. And that center of gravity is just going to be that center point where all our weight is focused. Where is gravity really forcing this plane to the center of the Earth? So we have center of gravity ahead of that center of lift. Why is it always ahead of that center of lift? Because if we did stall, we know stalls are all about reaching a critical angle of attack. If we stalled, we're going to experience a moment of decreased lift, and that center of gravity is going to go ahead and take over, and it's going to decrease the angle of attack for the plane for us. Aerodynamically, just bringing the aircraft out of that stall condition for us, which is kind of a safety design feature for the 172 at least. Now, if we're flying straight and level here and we have a center of gravity ahead of that center of lift, well, if we have nothing on this side of the plane, we would know that it's just going to go ahead and tip forward. That's why we have on the back of our Cessna here a horizontal stabilizer. This is basically an upside down wing that creates a pressure on the top to kind of balance this aircraft out. What they call this this force on the back of that horizontal stabilizer, it's a tail down force. So we have the tail down force countering that center of gravity ahead of that center of lift to go ahead and balance out this plank for us, or balancing out our Cessna. Also with the tail down force, they'll call it TDL, just for short. So we have three things here: center of lift in the middle. Center of lift actually moves a little bit. If we increase the angle of attack, it moves forward and gets closer to that center of gravity, making it less stable. and then we release pressure, it actually moves back aft to let that center of gravity go forward and recover from a stalled condition. We also have some ranges for our center of gravity, and we'll go through chapter 6 of the pilot information manual. There's some charts there that show the limitations of a forward and an aft CG, and we have to go ahead and operate within that envelope. It'll show how much weight for that certain envelope and how many inches forward and aft of datum we can be to go ahead and be within safe operating limitations for the aircraft. Now, this center of gravity can move forward or aft depending on how we're loading the plane. Are we putting more weight in front of the aircraft, or are we putting a bunch of weight in the baggage compartment? It's going to go ahead and move forward and aft. Now, there's some characteristics with a forward CG and a aft CG. So with a forward CG, obviously we have more weight on the nose of the aircraft. So if we're trying to fly out, we get to our cruise altitude and we're trying to maintain altitude. If we don't increase back pressure, we're not going to be able to maintain altitude. So we have to go ahead and increase the angle of attack for straight and level at cruise flight. Now, we know when we introduce more lift or we increase the angle of attack, we also experience more drag. So we're going to have a slower cruising speed with a forward CG. Now, so that's going to be one of the variables for the forward CG. We're also going to have favorable stall characteristics, like we already said. If we have a more forward CG, that nose is going to want to pitch down for us. If we increase that angle of attack past the critical angle of attack, it's just going to aerodynamically recover the aircraft for us. It's one of the design characteristics of the 172. So we have favorable stalls. And then we also have a higher stalling speed. So we know, say we're flying out at, our cruise speed's 95 knots. We are increasing that angle of attack to go ahead and maintain that 95 knots. If we go ahead and increase it further, we get closer to that critical angle of attack, and we're already at a high angle of attack. So when we go ahead and increase it further to that critical angle of attack, we're going to bleed off less airspeed than we would if we were more nose down. So it's going to have a higher stall speed. So slower cruise, higher angle of attack, increasing more drag, favorable stall characteristics if we do stall, nose heavy, and then a higher stall speed because we're already at a higher angle of attack at cruise. If we increase it to a critical, it's going to take less time for us to get there, not as much time for us to bleed off more airspeed, and we stall at a higher airspeed. It's very important to know that we can stall the Cessna or any aircraft at any airspeed. Nose up, nose down attitude. It's all about the angle of attack and that relative wind that's coming at us. So we can be super nose high or be super nose low. It's all about that relative wind and that the angle of attack. The difference between the relative wind and the chord line. Then we have the aft CG. So a little bit of an aft CG here. CG's working a little bit closer to that center of lift. So we're going to head and fly out at a lower angle of attack. So we have less drag on the airplane at cruise, so we are going to have a faster cruise. Now, with the aft CG as well, with the forward CG, we had those favorable stall characteristics. If we did go ahead and exceed that critical angle of attack, that nose heaviness is just going to drop that plane for us and decrease that angle of attack. If it's too far aft, it's not going to go ahead and do that. We'd have to give it some sort of forward movement on the elevator to actually decrease it to recover from that stall. If it's too far aft, we can actually experience a flat spin, and it could be unrecoverable. So aft CG is going to be less favorable stalls. And then we have a lower stall speed. So we have, we're flying at a decreased angle of attack as we would compared to a forward CG. If we go ahead and increase the angle of attack to that critical angle of attack, we're going to start bleeding off a lot of airspeed. So it's a lot more time for us to increase the angle of attack to get to that critical, bleed off all that airspeed, and we're actually going to stall it at a lower angle of attack, so a lower airspeed, or a lower stall speed. Now, just like for extreme cases, if we have too far forward of a CG, we might not be able to get it off the ground. It's going to take a bunch of back elevator force to even get that nose up. Even if we do get it up, we're going to have that decreased climb performance because we can't get the nose up, and it's going to be not a good day. So it's going to increase the ground roll on takeoff. Also with landing as well, we might not be able to actually start our flare, and you might just nose wheel it into the runway. So forward CGs, even though it's favorable stall characteristics, it can also hurt us if we go past these operating limitations, or the CG envelope for a forward CG. Now with that aft CG, we already said if it's too far back, we might not be able to recover from that stall. Also with an aft CG, if we're rolling down the runway and we take off, we might increase that angle of attack too much and stall it right above the runway. It might take a lot of force, a lot of nose down force to go ahead and maintain level flight if it's too far aft. So we really want to make sure we're going through Chapter 6 of the Pilot Information Manual, which we'll go through. I'll kind of do what I did with the first one, Part 1. We'll go through that PIM together, look at that envelope and make sure we're within that and we're not going to experience something like that. Cool. So we'll kind of brief Chapter 6, Pilot Information Manual, get a good idea what we're going to see, and then we'll jump on the handbook itself and go through it and do some sample problems and whatnot. But the biggest thing to take away from this is our center of gravity forward, is it aft, and what kind of characteristics we're going to get for this. So now there is some terms we have to understand before we can go ahead and jump into the book. So I'm trying my best to draw a side profile of the Cessna. And that's the best we're going to get there. Yellow propeller here. So how do we actually measure how far back our loading arrangements are in the plane? Because we have what we call in the plane stations. So stations are just going to be points on the plane. It could be passenger, it could be the rear passenger spot, it could be the baggage area 1, baggage area 2. It's going to be spots on the plane that we actually make measurements from to determine if we have a forward CG or an aft CG. And you'll kind of see it when you go through Chapter 6. They have a whole loading arrangements thing. It's organized with the pilot and the passenger, then rear passengers, and then it has the baggage compartments and whatnot. So we're I believe it's 4 different stations off the top of my head. Where are we making these measurements from? A datum, a reference datum. And just with the standard datum plane, this is just going to be a theoretical line that we actually draw distances from to see how much we're loading an aircraft and what kind of torque we're going to go ahead and experience at that loading spot. So standard, the reference datum is usually situated just behind the firewall of the aircraft, and we're just measuring from that datum all the way to the station how far the arm is, and then we're going to go ahead and find what kind of moment is actually taking place there. So the point from the datum to the station is going to be called a arm. We have this here, and also have the datum all the way to the baggage area, and it's just the horizontal distance we're actually measuring from. So we talked about the stations, we talked about the reference datum, we talked about the arms. Now we can talk about moment. Now a moment is going to be the weight that we actually have at this station multiplied by the arm. So this is going to be the torque force that we're actually experiencing at this station, which is going to affect how we find where our center of gravity. So the moment is going to be the arm times the weight at that station. So if we had 150 pounds here and we knew this arm, just for simplicity, we say it was 10. It would be 10 times 150, and that would give us our moment. And basically, we're just adding up all these moments and dividing it by our total weight, and we're getting our center of gravity. That's how we're kind of calculating this. Another thing as well is basic empty weight. We have standard empty weight, basic empty weight, but basic empty weight is going to be the actual weight of the aircraft plus optional equipment installed inside of the aircraft, also unusable fuel, and full fluid, so full hydraulic fluid and full oil as well. Basic empty weight for your aircraft is going to be found on our weight and balance. It's actually signed off by a mechanic. When we talked about required documents on the airplane, you go back to AARO, your airworthiness certificate, registration, radio operator's license, your operating handbook, and then your weight and balance at the end of that acronym. It's not the weight and balance that we're about to calculate. It's the weight and balance that is done by an AMP and is actually signed off by an AMP, and that's where you find your basic empty weight and then the moment for that basic empty weight. And we need that on the aircraft whenever we're going to go ahead and operate it. But that's going to be the base for what we're going to go over in Chapter 6 of the Pilot Information Manual. We're going to use a few different methods to go ahead and calculate our CG. So when we're going through Chapter 6 of the Pilot Information Manual, there's going to be 3 methods we use to calculate the weight and balance or the center of gravity for our aircraft. First one, being the most popular, is going to be the computational method. And that's going to be us going through each station of the aircraft, defining what weight we're putting at that station from that datum line, and then defining what sort of moment, what sort of torque force we're actually finding there. So we're going to get the weight, we're going to define the arm by the loading arrangement given to us in Chapter 6, and then we're going to find the moment. And then we're going to have the graph method, which is a little bit less accurate than that computational method. That's why I like the computational method. You're doing the math and you're getting more accurate numbers. The graph method, it's basically a graph inside of Chapter 6, and on the left or the y-axis of it, we have the weight that we're actually putting at that station, and then the x-axis we have the moment, and we just kind of go across to whatever arm is at that station, and then we read down and find that moment at that station. Which could be a little bit wonky. The graphs are kind of hard to use. It's a little bit older. You got to really make sure everything's lined up to get an accurate number. So I like the computational. And then we have the table method, which is just, I believe they have them for like bigger jets and whatnot. We can find that in the PHAC. I believe it's Chapter 10, and it's a good example of it. But if you have one in your pilot information manual, it just reads it out like a table. You have different amounts of weight for each station, and it reads and it just tells you straight up to the right of it what is that moment at that station. We'll start out with the computational method. That's going to be the most common one, and then we'll go through the graph just so you know where that's at, and we'll go through the table method inside of Chapter 10 just so you have an idea of what that looks like if you're flying something one day that has that table for you to use to go ahead and calculate the moment. But yeah, that's basically how it's laid out. So we have the datum line. We're making measurements from that datum line to the station. What is the measurement? It's the arm. We're going to go ahead and multiply that arm by the weight that we're putting at that station to find the moment that we're putting there, and that's the torque force that's actually occurring at that station. But yeah, we'll go ahead and jump over to Chapter 6 and kind of get a visual on what this actually looks like. Alright, so now we're back in the Pilot Information Manual. We're going to be specifically in Chapter 6. So Chapter 5 was all that good performance stuff. Now we are now in weight and balance section. So it's kind of be laid out like the performance one was. We'll go up to the top, table of contents. We have the introduction part, airplane weighing procedures, weight and balance. It's going to give us like some practice calculations we can do. And then our comprehensive equipment list. So if we go down through here, we'll just kind of skip over all this stuff, sample problems and whatnot. We'll go to the loading arrangements parts. So this is going to go ahead and tell us what kind of stations exist in the aircraft. We're going to have 4 different ones. We have the pilot and the passenger station, which is going to be right here. And then we have the rear passenger station right behind that, baggage area 1, baggage area 2. Those figures to the left of it are going to be the arms. So how many inches aft of the datum or that reference line behind the firewall do these stations actually exist? So for the pilot and passenger, we have 37. In parentheses, it says 34 to 46. That's because we have adjustable seats that move forward and aft. So that would obviously change how far we are from that datum. So we have to be cautious of that. If we're kind of in a middle seat positioning, we just find a number in between that. We could use 40, 39. to go ahead and be a little bit more accurate. Then we have 73 for the rear passengers. Baggage area 1 is 95 to 108. Now there's a couple asterisks next to 95. That is letting us know that if we read the notes up here, that the max weight we can have at baggage area 1 is going to be 120 pounds. So 95 to 108, baggage area 1. And then baggage area 2 is going to be the arm 123 to 142. We also have some asterisks next to 123 that's letting you know that we cannot exceed 50 pounds in baggage area 2. And this is all going to be listed in the notes. So if we read the notes up here, the usable fuel CG arm for integral tanks is located at station 48. So fuel has weight. It's not showed on this loading arrangement graph, but we have to know that the arm for the fuel station is 48. The rear cabin wall, approximate station 108, or the aft baggage wall, approximately station 142, can be used to convenient interior reference points for determining the location of the baggage area fuselage stations. So that's basically going to be laid out. We have the stations, and now we have the arms. And we know if we multiply the weight that we actually put at these stations times these arms, we're going to get the moment or the torque force that's actually happening at that station. So we can go back here. I kind of got a sample weight and balance sheet. So for your check ride's sake, you don't want to be using the electronic one. You kind of want to show your work with your examiner. I mean, you could. It's just better to use, pencil, paper, show your work, what kind of math is going on, how would you get these figures. But it's going to list it out. So we have the stations to the left. So we have pilot 1, pilot 2, passenger 1, passenger 2, baggage area 1, baggage area 2, the fuel load, fuel burned on the ground, fuel burned during flight, and then the landing condition. So we want to make sure within this CG envelope, or this envelope that looks something like this up here, we're within this green, and we're not too forward from it, and we're not too aft of it. If we're on the forward side, we know what happens with the forward CG, and when we're on the aft side, we know what happens with an aft CG. We just went over the characteristics of those. So we can kind of start this here, the basic empty weight. So if you noticed when we went through the loading arrangement sheet, it said nothing about the basic empty weight. What is that? That is information that you can find specific to your aircraft on a weight and balance that's signed off by an A&P. So the mechanic actually calculates this for yourself, the basic empty weight, and then the moment that's actually going on there. So it has to be specific to your aircraft. It's going to give you that basic empty weight. We went over what basic empty weight was. It's going to be the weight of the aircraft itself. Also the optional equipment installed. It's going to be the unusable fuel. And then it's going to be full fluid, so full hydraulic fluid and full oil. That's what basic empty weight is counting, and that's kind of where we're starting these calculations. So we'll start at pilot 1 here. So I weigh, 210 pounds. We'll call it with clothes, shoes, whatever I'm wearing. Let's call it 215, just to be conservative. Whenever we're thinking of these numbers, we want to be really conservative with it, just to make sure that we're within this center of gravity envelope. And then pilot 2, say I was flying, with you, a student. Let's say you're 180 pounds. We'll go ahead and toss that in there. Now we'll go over to the arm. It already put us at 37 for the arm. We're just going to go back to that loading arrangement sheet and make sure it's accurate. So the pilot and passenger is right at 37, but we have to know, if we're super forward, if I have a tall student or a really short student, that's going to vary from 34 to 46. So try to be a little bit conservative. For this, just to make it simple, we'll just use the 37, but make sure if you have, a 6'7" passenger, they might be more towards this 46 because they really got to push that seat back. So now we'll go back to the sheet. So we got 215 for me, 180 for you. Now we have the basic condition, 2,093.8. And we know our max gross weight is 2,550. So we're under max gross weight right now. So far, so good. Now we got to go back to the rear passenger seats. So let's say, we didn't have any passengers today, but we had some weight back there. Let's say we had some luggage. We had, you brought your P-hack in today. You brought a couple handbooks. You brought some notes. You brought a backpack. We're doing a longer cross country with a water bottle in it, maybe some snacks. Let's go ahead and add 25 pounds just to be safe in the rear passenger seats. And then for the passenger 2, we'll just go ahead and put 0. Now for the arm, we have to make sure that it's actually 73. Rear passenger seats don't move around.
So it's going to be 73 according to chapter 6 here. So we'll just bounce back. All those numbers look good. And basically what this chart here is doing for us, you'd actually calculate this out with an actual calculator. We're taking the weight and we're multiplying it by the arm found in chapter 6, and we're getting a moment. So 1,825 pounds of torque force there at that station. And then we're kind of just taking all these moments that we get in the column over here, and we're going to divide it by the total weight of the aircraft, and we're going to get a CG. And it's going to be somewhere on this graph here. That's kind of what we're doing. So passenger 20, we don't have any other passengers. Baggage area 1, so it's going to be, I believe it was at the 95 arm, which they have already listed out. Let's say, hey, we had a couple empty oil cans back there. I know we have the tray, maybe it was a funnel. Let's just add 5 more pounds of weight. And then baggage area 2, it actually already takes into account the tow bar. So the tow bar that's all the way back after the plane in baggage area 2 is already taken accounted for in the basic empty weight actually. But hey, let's go ahead and be conservative. Let's add another 5 pounds. Maybe there was something back there that we had to load. Maybe you had another backpack or some more luggage that we wanted to toss. We're just going to make sure these arms are right. So they have 95 and 123. We'll go back to section 6. Baggage area 1 is going to be 95, and it really depends on how we load it too. If we're on a climb, it might roll back to that 108, so you might want to be a little bit conservative on where you put that arm for the calculations. And baggage area 2 is at that 123. We'll just keep it at those for simplicity, but depending on the type of object you have back there, we want to make sure that everything's secured and loaded correctly so it's not moving around. If you were put a bowling ball at baggage area 1, you really want to make sure that's not moving around, so it's constantly going forward and aft and changing where that center of gravity actually is. So we want to be loading everything properly and make sure it's not moving around. It can also be a distraction towards us. So, but let's say it's just in a fixed position on the most forward part of baggage area 1 and a fixed position on the most forward part of baggage area 2, just for simplicity. Then we'll go back here to the calculator. Everything's good. Arms are all lined up, 95, 123. We put 5 pounds for each just to be conservative. Now let's go to fuel load. So we know that basic empty weight already takes account the unusable fuel in the aircraft. So the most fuel that we can put inside of the tanks is 53, because we know we have 56 gallons for those 2 tanks total, but 53 is useful, or is the most usable that we can actually use. So we put 53 here, even though we know the 3 pounds are already taken account for. Let's see, we're doing a longer cross country, so we wanted to fill up those fuel tanks today. And then we have an arm of 48. If we go back to the notes section in the loading arrangement, that's going to be the first note. Usable fuel CG arm for integral tanks is locating at station 48. So that's kind of how we're lining it up here. Now, our ramp condition is going to be below that. So something I didn't mention was the zero fuel condition. So that's basically the weight of the aircraft without us putting any fuel in it just yet. It was 2,128 pounds. And then the total moments we have at the moment is that huge figure right there. Now we're going to ramp condition. So our max gross weight is 2,550 pounds. The max ramp weight, though, is 2,558 pounds because the pilot information manual or the manufacturer is assuming that we're going to burn at least 8 pounds on the ground of fuel for startup, takeoff, and taxi. So we'll just use 1.4. They want us to use 1.4 in the pilot information manual, but say you're on the ground and it was an instruction flight and we were just going over our run up. Maybe we were told to hold short of the runway for a while because ATC was coordinating people. So if we're longer on the ground, we can use a higher number there, go up to 2. I usually use 2 for my calculations just in case. But 1.4 is going to be the standard one that they want you to use. So now we have takeoff condition. We're under max gross weight, 2,438 pounds, and our total moment at the moment is that huge figure all the way over here. Now we can go to fuel burn during flight. So this is going to be in our calculations when we actually do our NW craft or 91-103 pre-flight action. We have to understand how how many gallons of fuel are actually going to burn for the flight. Let's say this is a 2-hour flight today, and on average we burn about 10 gallons per hour. So let's say we burn 20 gallons of fuel. We're going to multiply this by 6. That's something I forgot to touch on. The 100 low lead that we use is 6 pounds per gallon that we use. So that's why it's multiplying it by 6 there. So 20 times 6, so it'd be 120 pounds at the arm of 48. So let me just adjust that there. And now it's giving you the landing condition. So it's also making sure when we're in the landing condition that it's going to be 2,318 pounds. So we're under max gross weight. And then we have 95 to 11 for the total moment. Now we have our center of gravity. So we have our takeoff condition, which is going to be 2438.4. If we divide that by our total moment here, that 100,971, we're going to get a center of gravity of 41.41. A way to memorize that center of gravity calculation is going to be mom over weight. So your moment divided by your weight is going to be your center of gravity. Now, I've never used this one before, so I want to make sure that this is correct. This is not the envelope that is used for our aircraft, so we're going to have to jump into the pilot information manual to make sure that we are within the CG envelope, not too forward, not too aft, and we're also within those weight limitations as well. So let's jump into Chapter 6. Go ahead and scroll down here. This could be a sample problem. Now we have the weight on the y-axis here, and then we have the moment on the x-axis. That one's a little bit hard to read because you saw how big that moment figure was. Let's go ahead and see the one that it compares to weights to center of gravity. So we have the weight on the y-axis and we have the center of gravity on the x-axis. If you notice here at the top of the envelope, it's going to be 2,550 on top of these black lines here. That's because we can't exceed that weight. That's our max gross weight. So we have a normal category and we have a utility category. Normal category is just going to be for normal operations. Utility category is going to be for limited acrobatics. So for per the pilot information manual, we can actually do spins if it's in furtherance of gaining a certificate. Like a flight instructor, you need a spin endorsement from an instructor. So we can go ahead and make sure that we're within the utility category envelope before we actually go out and do spins, so we make sure that we don't overstress the aircraft and we can actually recover from the spin by not being too far aft. So we kind of see our forward and aft limits here. We have a forward limit of 35 inches aft of datum for the center of gravity, and then we have a aft limit of about 47 and a half, we'll call it, for the aft center of gravity. Now we can go back to our figures, make sure we're within both of them. So we know our takeoff condition was 2440, we'll call it, which we know is under the max gross weight, so we're good there. And then we have a center of gravity of 41.41. So let's go back. 41.41 is going to put us right through here. And if we go up to 2440, it's going to put us right around here for our takeoff center of gravity. So we know we're within the envelope and we're operating safely. Now let's look at the landing one. So after we burn fuel, we go to landing condition, 2318, let's call it 2320 for simplicity, and then our center of gravity is 41.7. So it moves a little bit more forward when we start burning all that fuel. So 2320, 41, we'll go 41 here, and we're just going to go up to 2320, and that should put us right around here. So we're still within that envelope. I wish I could mark it so you could actually see it, but we know that we're within the normal category. We're within the operating limitations of the forward and the aft CG. A little bit more on the forward side today, which is completely fine. But that's basically how we're going to be reading these graphs. We're going to find the center of gravity by going through those computations, and we're going to find the weight, and we're just going to line it up and make sure we're within that envelope. Now, that's going to be the computational method. If we go up to this graph here, this is the graph method. So some people find this easier. I do not, because you kind of got to line it up. But we're basically, you see the lines in the middle, those are each station. So we have pilot in front, passenger, that's going to be station 1. We have fuel That was station 48, and then or the next station, which is the arm for it, is 48, and then we have the rear passengers, and we're just kind of going to read it. So if we had pilot and front passenger was a total of 200 pounds, we just go to the right, and then we go all the way down, and we read that looks about 7 for the moment, but that's divided by 1,000. So we'd have to take 7 times 1,000 to actually get our moment at that location. So that's kind of how you do that graph method there. Now we also have the table method. If we pull it up, let's go section 10. Of the Pilot Handbook of Aeronautical Knowledge. If we go down here, this is going to be the table method. So it's going to be this big guy here. So bigger jets and whatnot, they kind of have this for simplicity. But it's letting you know we have front seats here. So occupants, front seat arm, which is going to be 85. Whatever weight we put there to the right, you just read the moment. Rear seats, arm 121. Whatever weight we have there, you just read the moment. And it just has it for everything. It has oil, weight there, moment, and that's kind of how you read it. I feel like it's a little bit less accurate. You can't be as precise with the weight, and it's just kind of harder to read for me. But hey, if it works for you and you have one specific to your aircraft, meaning its tail number, then by all means use it. I just find the computational method being the bare roots way to go ahead and knock out the weight and balance. And it's a little bit more accurate because you're actually doing the math. You just got to make sure you're doing the math correctly. Let's see here if I wanted to touch on anything else about these. Yeah, that's basically be section 6. So just in review, when we go back through here, basically what we're finding is we're finding the weight we're loading at each station, and we're also finding the arm for each one of those stations as well per chapter 6 of the pilot information manual, and we're just multiplying that to find the moment. Once we find the moment, we can go ahead and add that up and divide it by our total weight, and then we get our center of gravity. And we're just making sure we're within that center of gravity envelope, which is shown to us in chapter 6. If we go all the way down here, chapter 6. And yeah, we're just going back to this graph here, and we're just making sure we are within this center of gravity envelope here. You can also set up your ForeFlight. There's a bunch of good videos on how to set that up. So you just add the weight you're putting at each station, and it graphs this for you on ForeFlight. But we have to understand what this is actually doing for your check ride. Please print these sheets out, write it out, actually dot where your center of gravity lies for the simulated flight you're going to be doing with your examiner, and just explain what kind of characteristics, forward or aft, and also weight change. So that's something that we'll touch on in the next video here. I'll kind of the next section. What is going to happen when we move weight forward or aft? If we shift it around the aircraft, what if we add weight? What if we add another passenger? Where's that center of gravity going to lie? And there's some calculations we're going to do to get a good idea of that. But yeah, 2 kind of methods here. We have the center of gravity envelope here, and then we have the one that I kind of find harder to read is the weight to the moment, and then we just make sure we're within this envelope. Practice on both just to make sure you understand, but that's going to be the basics and how to use these graphs in section 6. So that's going to be section 6 of the pilot information in a nutshell, weight and balance. The biggest thing that we want to go ahead and take away from that is we have an envelope that exists for the aircraft, and we don't want to be too forward of that envelope, too aft, and we don't want to go over the max gross weight. Where you have it too forward, we're not going to go ahead and be able to apply enough back pressure to even get the aircraft on the runway, which is going to increase our ground roll, increasing the risk of us actually hitting the obstacle or obstruction at the end of the runway. Also, if we go ahead and get it off the ground with forward CG, we're so much back pressure, adding so much drag, it's going to go ahead and decrease our climb rate, and we're not going to be able to climb out efficiently. Same thing if we're coming in for landing and we want to go ahead and execute our transition into the flare. We might not be able to do that. We might just nose wheel it into the runway itself.
with the AFCG, we want to make sure, you know, if we go ahead and do take off, if we're behind this AFCG envelope, it's going to go ahead and keep increasing that angle of attack to a stall, and we will stall spin on takeoff. Also with an AFCG, if we're at altitude and we do encounter a stall, we know that center of gravity's closer to that center of lift, and we're not going to be able to get that nose down. So that's going to be a flat spin, and it's going to be unrecoverable, and unfortunately, it's not going to be survivable. And then max gross weight, we don't want to fly anything over 2,550 pounds. This is going to obviously increase our ground roll on takeoff and landing, decrease our climb performance, and overstress the aircraft. A lot of people do this, you know, there's case study after case study of people doing it, and you know, they say they get away with it, but it's just constant wear and tear on the aircraft. It's going to decrease its performance, and then one of those days, you're going to snap off those wings, or something else on the aircraft is going to fail on you. So that's a gist of Section 6. We want to make sure we're within that envelope and we're operating the aircraft safely. Now we're going to wrap up performance and limitations with some written exam problems. So on the written exam, they have a few different problems they want you to go ahead and knock out. So it's going to start with, you know, adding weight or subtracting weight formula. We have to go ahead and find the new CG, and then we're going to have a weight shift formula. We're moving something from one station to another station. Where is that CG going to move on that envelope, and are we still within safe operating limitations? So with this first one here, it's going to be kind of laid out like this. So we have the weight of the aircraft, which is 6,860. For some reason on the written they use big jets, so it's not really applicable to the little Cessnas flying around. And then also a CG of 80, which we already went over. Our envelope, it's not that high, but this is what it's going to look like on the written. So locate CG if 140 pounds of baggage is added to station 150. So we're adding 140 pounds of baggage to a new station. Are we still within that CG envelope? So we're going to go ahead and break down the formula here. So weight shifted divided by new total weight is going to be equal to the change in CG divided by the station minus the old CG. So it's going to kind of look like this. Weight shifted, we know we're taking 140 pounds. We're going to divide that by our new total weight. So we're adding weight. We're going to go ahead and do, so it'd be 140 plus our 6860 would be about 7,000 pounds. Is equal to the change in CG divided by our station, which is 150 minus 80. So we're adding 140 pounds to station 150, not actually shifting weight. Weight added should be the actual one here. So weight added or subtracted. So it's going to be 150 minus 80, which is going to be 70, and we need to multiply that by 140. So let me just knock that out real quick. 70 times 140 is going to be 9,800. And this is going to be equal to 7,000 times the change in CG. Now, how do we actually get the change in CG now? We're going to have to divide by 7,000. So it's going to be 9,800 divided by 7,000. And then we're going to get 1.4. So this is telling us that our CG is going to change 1.4 inches. So we need to go ahead and add that to our original CG, and we'll get a new CG of 81.4 inches of datum. And then we'd have to go ahead and go in section 6, look at the envelope, go ahead and make sure that 81.4 inches of datum is actually within the normal or utility category, and make sure it's, you know, it's a safe center of gravity for us. So that's going to be weight adding or subtracting. If we were subtracting, we get a negative number. We know we just add that to our original CG and it would move forward. But that's kind of how that works. So now we have a weight shift formula. So we want to shift 100 pounds from station 100 to station 150. So the weight to be shifted divided by the weight of the aircraft is going to be equal to the change in CG divided by our new CG location, or new station location, so new station minus the old station. So the weight to be shifted here, we already said in the example here, it's going to be 100 pounds. And we know the weight of the aircraft is going to be 6860. So we'll go ahead and write that in here. That's going to be equal to the change in CG divided by our new station minus the old station. We're going from 100 to 150. So it's going to be 150 minus 100. So it's just going to be the difference between the old and the new station. So 50 times 100 is going to equal 5,000. And that's going to be equal to 6860 times the change in CG. Now we can just divide 6860, 6860, 5,000 divided by 6860 is going to equal 0.73, we'll call it. So this is letting us know if we go ahead and move it to that station 150 spot, it's going to move 0.73 inches of datum. So we go ahead and add that here to our original CG, which was 80, and then we're going to get a new CG of 80.73. We'll call it 81. Go ahead and round up. And that's going to be our new CG location if we went ahead and took 100 pounds and moved it back to station 150. So that's going to be the example problems for the written. You'll get plenty of those, so make sure you go ahead and practice that, get those formulas down. But yeah, that's going to be performance and limitations. We talked about, just in review, what changes air density, how that affects your performance, and how we can use calculations to tell what the aircraft's going to feel like, or feel like it's taking off at for a given day, and how those conditions change. And then we went through section 6 of the weight and balance. Make sure you actually get a sheet for your check ride. Go line by line, station for station, arm for arm, and make sure that we're always operating within that CG envelope, not too far forward, not too far aft, and we're not over gross weight. Like I said, this is one of the most important sections of any of the technical subject areas because there's just case study after case study of people overloading aircrafts, going too far forward, going too far aft, and that's going to result in loss of life. So make sure we understand this, practice, 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 get all those performance calculations down, go through those weight and balances, and it's going to make you a very safe pilot. So thank you so much.